Hi, it's Peter. Sebastian's taking a rare vacation day today, so I'm going to be answering the questions myself. We had a bunch of really great questions again from all you students out there, so let's go through some of them. The first one's from MRLED in London, and he asks, what's the normal path for a professional in AI? Assuming you come from university, what sorts of roles in industry can be pursued? There's names like developer, games developer, computer scientist. Are we more than just that? And then related to that question is one from Sasha in Hamburg, saying, I'm in love with AI. However, given my age and lack of degree, it seems hopeless to get a job in AI. Is it too late for a mid-30s to jump onto the AI bandwagon? And I guess I'd have to say that there are many paths. Another title besides the one mentioned would be research scientist, but usually that's for somebody with a PhD. I see the title data scientist showing up now more commonly, but I would say that most paths involve being a computer scientist or a developer who has some AI expertise and gets to use that on the job, but doesn't define themselves only by being an AI developer. So you got to be able to get the job done no matter what the tools take. But it's great to have that AI expertise as part of your toolkit that you can apply to your job. I should also note that my colleague Hal Varian at Google has stated that he thinks that the sexiest job in the next 10 years will be statistician. And in some ways, statistician and machine learning person overlap quite a bit, so you're in good shape there. Let's see. The next question comes from New York City. How has your experience of the continuous flow of data from quizzes and homeworks changed the way you teach this course? And will it impact how you teach in-person courses? Well, I got to say, we're doing our best just to keep up day to day, so we really haven't had a lot of time to do a complete quantitative analysis of all the data that we get, all the click streams and the answers to questions and so on. We'd like to do that. We haven't really had a chance yet. We've got sort of an impression overall from the quizzes and homeworks and from all the discussion forums. It tells us a lot about what works and doesn't work, and overall, I guess one thing that comes through is when you have 1,000 times more students than you're used to, there are 1,000 times more ways to misunderstand and get some assumptions wrong. And we feel bad whenever there's confusion over that. So we're learning to be more careful. But still, I'd like to take this chance to say that the point of the quizzes and the homeworks is not really just to see if you can get 100% right. If you can, that's great. But the point of the quizzes is for you to think deeply about the problem. And in some ways, if you find the problem confusing and it forces you to think about it, then you've really done more work than somebody who doesn't see any ambiguity and answers right away. So if there are ambiguities, I apologize and I feel bad about that, and we'll use the learning we get from all of you to do a better job and try to eliminate those ambiguities. But if it makes you think about the problem more deeply, and if you discover something that others didn't, then I'm not apologizing for that, because really what we're trying to do is to get you to engage with the material as much as we can. Next question is from Geneva, Switzerland. What books would you recommend to read after the end of the class? And I guess I would say there's a lot of recommendations. I don't want to go through all of them now, and I've written up some of them already, so you can search online for Peter Norvig's library Google Books, and you'll see a list of books that I've pointed out there, and some of them I've actually written reviews for. And there's several lists, and they're broken out by different categories within AI, so it all depends on what you're interested in. Natural language, planning, vision, robotics, learning, all the different areas are there, and you can choose the ones you're most interested in. Next question is from Pombo in Buenos Aires. It says, hi, is there any relation between Markov decision processes and game theory? They seem to have something in common. And that's a great question, and it's one that came up in the class at Stanford as well. We've shown several approaches to planning actions. We started out with state-space search, which works best for deterministic and centerless domains. And then we got into classical planning. It works with more abstract and complex representations. We added the ability to do sensing to that, to go beyond classical planning. We talked about MDPs, Markov decision processes, to deal with stochastic actions. and game theory to deal with adversaries. Now, each of these fields have historically developed separately, and they have their own vocabulary and their own methods of working, and they attack different parts of the complexity of environments. But when you start adding on, we go from classical planning and you start adding in stochastic and sensing and so on, then they all begin to merge. And when you add all the features back in, they all arrive at the same place. And so the historical differences seem to dissolve a little. So the nomenclature is still different, and that makes it confusing. I apologize for that. And the different approaches have their different highlights. They are good in different things. So take, for example, MDPs seem to be good for things like a robot navigating around a room, where the robot could very easily get from one spot in the room to another and could come to the same spot multiple times. So that you could say that the state space is rather dense, and that it's easy to get from one place to another. Now compare that to a game tree search or game theory. Take a game like the game of Go. If we put a black stone down on one point, now we've really kind of partitioned the state, and so now we're only in the part of the state space where there's black on that point, and not on the part of the state space where there's white. Now, it is possible in Go to flip from one to the other. You could capture that piece and then replace it with the white one, but that's rare. So really in Go, you're exploring deep, long trees that don't have many circles back to the same position, whereas in robot navigation, it's almost the opposite. And so that's why we have different techniques, even though they're very overlapping in what they end up covering. I hope that maybe someday there'll be a unification of all these different techniques, and that we'll understand all the best parts of all of them and be able to express one in the notation of another and make it all work. And maybe one of you students out there will be the one who ends up doing it. Let's see. Another question about MDPs comes from Germany. You showed some videos of robots when introducing MDPs. Actually, what are the stochastic actions? I can't believe one really treats the movement of a robot in a stochastic way. And even if so, how small or large do you choose your grid? So yes, the movements of real robots are in fact stochastic, but we exaggerated that in the examples we gave. So it would be very rare to have a robot that's so bad that 80% of the time it goes straight, but 10% of the time it goes in a 90-degree direction in the wrong way. So robots don't go off that bad by 90 degrees. But if you ask a robot to go forward 1 meter, it's very rare that it would go forward exactly 1 meter. Maybe it'll go 95 centimeters or 106 centimeters. And maybe it won't go exactly straight ahead. Maybe it'll go 5 degrees to the right or 2 degrees to the left. So these actions are all stochastic, if not to the degree that we showed them. Should also say that there are stochastic changes to the environment. Say a person or another object might appear in front of the robot, forcing it to stop. And the percepts are very stochastic. Take like a LiDAR rangefinder. Now these are very precise instruments, and they can give measurements up to a few millimeters, but not every percept that they give back is accurate. Some of them are wildly off, and we have to use techniques like filtering to make sense of those. Let's see, the next question comes from Fargo, North Dakota. When I tried to implement a reinforcement learning agent, I encountered an issue. The agent takes too long to reach the absorbing state, and hence doesn't learn anything for a long time. And sometimes it never stumbles upon the absorbing state. Any remedies? Well, that's true. In problems where there are no rewards along the way, when there's only a final terminal state, and where the number of terminal states is small compared to the total number of states, it can take a really long time to learn anything. And one remedy is just try harder, run more steps. Don't be afraid to do millions of steps rather than thousands of steps. And another is to use an initial policy that's not completely random, but is somehow guided toward these terminal states. And if you don't know where they are, then use an initial policy that's more exploratory to cover the full state. And then once you find your way, then you can try to bias the policy in that direction. Let's see. Here's a question. Is the update in value iterations simultaneous, like the AIMA book says on page 653, or not, like the video 917 seems to imply? And that's a good question, and it turns out both approaches have been used, and they're called synchronous and asynchronous value iteration. And the initial theory is around the synchronous, and that's what the algorithm in the book is about. But you can also do it with asynchronous. It took a little bit longer to work out all the proofs, but asynchronous converges as well, so you have a choice. Here's one from Hamburg. A utility function U resembles a heuristic function in being an estimate for the ways ahead, whereas the notions of utility and cost are complements. Shouldn't utility be designed to never underestimate, just as an admissible heuristic never overestimates? Well, I would say that a utility function is not like a heuristic, in that the heuristic is something that you invent to help you solve the problem, where the utility is really given. It's you could think of it as part of the problem, or you could think of it as really being part of the agent itself. It's built into what the agent wants and when he wants it. So the when he wants it part, or when it wants it part, has to do with the discount factor. How much do you weigh off rewards now versus rewards later? But that's sort of an intrinsic part. It's not something that you can play around with. It's not an estimate. It's more of a definition of what the problem is. Here's a question. I'm now inspired to learn more about POMDPs. Do you have any suggestions for books, articles, or exercises? And that's from Zim in Chicago. I guess I started, and a lot of people really did, with an article in 1998 by Leslie Kelbling, Mike Littman, and Tony Cassandra, called Planning and Acting in Partially Observable Stochastic Domains. That was from the AI Journal. So that's a great place to start. Then you can look in the AIMA textbook, and you can search online for POMDPs, and there's a lot of information available.